one of the days today was reach as high as you can. Didn't make any sense. And I heard big cheese this morning when I was making my breakfast. And I said, yeah, I didn't choose that. So today instead, I chose, and of course I wanted it to be sunny today, but not. Today I chose to look up at the sky. Unfortunately, looking up at the sky is it'll be better. Okay? All right, so you do need a calculator, and if you are borrowing one of our calculators, I strongly recommend that you don't trust whoever was before you using it, so you start just a brand new program. You should be doing that every time you grab a calculator, either in here or in the Resource Center when you open it up, because you don't know what that person was doing before. Okay. One other thing too that I mentioned in the last class and is if you don't have your own graphing calculator, then you always have Desmos to fall back on, and you can do parametric equations on Desmos with that too. So okay, so just so you know. So before we begin today, I do have one little clip to show you before we start. That is important to our first example.
Hi, my name's Alfred D'Elia.
The audio didn't come. All right, here we go.
Hi, my name's Alfred D'Elia. At home they call me Big Al, and I hit dingers.
And I hit dingers. All right, so with that being said, we are on page, I believe it is 7, if I'm not mistaken. And Big Al is going to try and hit a dinger. Okay? All right? So Big Al hits a ball at an angle of 28 degrees with an initial velocity of 75 feet per second at a height of 3.5 feet. Will that ball that he hit under those conditions be a home run if the ball follows the left field line where the Little League fence is 190 feet away and 4 feet tall? Okay? So we have to come up with two parametric equations here for this one. So our first parametric equation that we're going to come up with is going to be the ball. I wish that was there, but that's right. We'll cover that up. Okay? There it is. I do like using the stylus better. So the first one that we're going to come up with is the ball. Okay? Now, refreshing our memories from last week, our x of t equation was going to be v sub 0 times the cosine of theta sub 0 times t, and our y sub t equation was going to be negative 16t squared plus v sub 0 sine of theta sub 0 times t plus h sub 0, where v sub 0 is our initial velocity, theta sub 0 is our launch angle, and h sub 0 is our initial height. Okay? So if we make an equation for the path of Big Al's baseball, our parametric equation, oops, I put a parenthesis around x, I didn't want to put a parenthesis around the t. X of t is going to equal, our initial velocity was 75 feet per second times the cosine of 28 degrees times t. Our y equation, negative 16t squared plus 75 sine of 28 degrees times t plus 3.5. Agree with me on that? Only thing left to have is a T value or a T range. What do you think T ranges would be for this one? For Big Al hitting a baseball. What are we going to start? What value of T are we going to start with? 0. Okay. All right. And how long do we think that ball's going to be in the air? 3 seconds-ish. Okay. If it's longer than 3 seconds, we can always adjust it at the end, or we can adjust it in the graph to make sure that we got it. Okay. Everybody good with that one? Okay. Then on top of that, we need to come up with a parametric equation for the wall. X of t is going to be what for the wall? In a parametric equation, the x is the what part of the object? What part of the parametric equation does the x function represent? Just what do you mean by distance? So how far away it is? Okay, so how far away is the wall? 190 feet. So the x parametric equation would be 190. Okay. What is our y value going to be? What do you got? But if we just do 4, then it's just going to put a dot at 190, 4. We won't be able to actually see the wall. Okay? I like what you're thinking, but that's just going to be a dot, probably hard to see. So let's actually build a wall. Let's call it T. Okay? If I call that T, then my T values are going to go from 0 to 4. And here in this case, when you're building a wall or some kind of a barrier in your parametric equation, your T is not time. Your T is feet, how high you want that structure to be. So in this particular case, we want that structure to be 4 feet. Now, we could have done anything there. We could have done 1/2 T, and then we would have had 0 to 8 be our T range. We could have done 4T there and gone from 0 to 1, okay? And so on and so forth, okay? As long as the maximum of this one is 4. Okay? So at this time, input that into your graphing calculator and tell me if Big Al hit a dinger or not. So when I type mine in, I get this. Can't see it, so we got to adjust our window. Okay? So let's adjust our window. X is our horizontal distance that can stay -10. We need to go out to at least 190 feet, so I'm going to go out to 220 feet just so I can see it. And I don't think it's going to go higher than 40 feet. In fact, it goes barely above 20 feet. Did Albert, young Albert, hit a home run? No home run for Big Al in this one. Okay? All right? My extension question to you is, what I would like you to do now is figure out, we'll go whole numbers only on this one, figure out what's the smallest exit velocity of the ball, so this 75 number, what's the smallest that can be to actually hit a home run. So you're just changing that 75, hit tab and scroll up and change that 75 until he actually hits a home run. What did we find for the smallest value of exit velocity that would then make a home run? Because the red thing's the wall. 86. Yep, 86 is the smallest, or how hard he would need to hit it under those conditions to actually hit a home run. Showing you, so you go here, and then tab, and go up here to 86, and 86, and there it clears the fence. Okay. Last class they traced it, and it went over. It went over by half of a foot. Okay. All right. Good job. Let's move on here now. I believe this is on the next page, if I am not mistaken. Actually, no, I lied. It's at the bottom of the Alfred D'Elia page. Yep. Okay. So how far can Jordan Love throw a football at an angle of 58 degrees with an initial velocity of 36 feet per second and an initial height of 6 feet? Okay. So, what are the parametric equations to go along with this one? Okay. And negative 16t squared. Okay. How long do we think that ball is going to be in the air? 10? That's fine. As long as we're over, it doesn't matter, right? Right? Okay. How are we going to know when that ball hits the ground? When it hits the x-axis, right? When it intersects the x-axis. Okay? All right? So let's graph this one. So this is the parametric path of the ball. Yes? Okay. So it throws it goes up, and then comes down. All is well there. Okay. But we want to know, the question is, how far? So that is my question. How far does that ball go? Okay. So let's go back to our graph. Now, brainstorm how we can figure out how to do this. One option would be to figure out how far it is. Well, first off of our graph, what are we looking for? When it hits the ground? Okay. So we're looking for this point right here, and what part of that point are we looking for? So which part of that point? The x part of that point, right? Okay. So how can we do that? Let's figure this out. Okay. And then what? Because we're in a parametric equation. What are my options? Option 1 is, what can we do? We can do what? We can trace it. Okay? Okay? Let's trace it. So that's menu, trace, graph trace. Right? Okay? So we can trace it, and it can come along, and the ball is flying. He's not throwing it to Dontavian Wicks because Dontavian Wicks just got traded. But what's the problem with the trace? It doesn't give me an actual y equals 0 value, right? Okay, so let's stay in the trace. What can we do to see if we can get a little closer to y equals 0? I plug in what? We can't put in y equals 0. The only values we can put in are t values. One option that we could do is we could go back into trace, and we can adjust this trace step. Okay? Right now, the trace step is set to automatic, and for automatic, it goes by 0.1. Okay? So we need a number smaller than 0.1. Let's say 0.05. Now when I move my cursor left and right, now it's going by 0.05, still getting a little closer, but not really getting much closer, right? So let's go by 0.01. Menu, trace, trace step. Pretty close, yes? Yeah? Okay, so we're pretty close. So if you're willing to take that chance, okay, you could say, here I would say 39.871 feet. Okay? Okay? That's one option. Get as close as you can to it. Okay? Okay? Option 2 is a little more involved. Okay? So option, but more accurate. Okay? So option 1, the trace, is quicker, but less accurate. Okay? Option 2 is more involved and more accurate. Okay? Which option do you think we would like to go with? Option 2. Okay? Okay? Option 2 says that what you're going to do is, what I'm concerned about is how far that he threw the ball. And I know how far he throws the ball when the ball does what? So he throws it. How do I know when the ball has reached its maximum distance? Hits the ground, right? Okay. What part is hitting the ground? Y=0 is when it hits the ground, right? Okay. So the height is what I'm concerned about. The ball is gone its maximum distance when the height of the ball is 0. Which part of my parametric equation is the height of the ball? It's the y part, right? So what I'm going to do is I'm going to create a new document. Okay? So that's control dot. I'm creating another page on my calculator, and on that page I'm going to add a graph. I'm going to take just the y function and I'm just going to graph it, because we can't analyze in a parametric. We can't do any of our analyzation in a parametric. It's one of the downfalls of the TX. Okay? So what we're going to do then is we're going to take our function, -16. Now it was -16t squared, but this is a function of x, so I've got to change this over to x squared plus 75. No, not 75, excuse me, that was Alfred. 36 sine of 58 degrees times x plus 6. -16x squared, 36 sine 58x plus 6. And when I graph that, I can find certain things. So now on this particular graph, I can analyze it. So the first thing that I can analyze it for is I can analyze it for the maximum. I can figure out that the maximum height of this Jordan Love football was 20.563 feet. And that happened at 0.954 seconds. Okay. I can also analyze this graph for a 0. And that this ball hit the ground after 2.087729 seconds. Okay? Get that on where I can draw on it. Oops. So option 2 then So what this is saying is that is my maximum height. So 20.564 feet at t equals 0.954 is my maximum height. Okay? This is telling me that the ball was in the air 2.088 seconds. Okay? Because that is where it hits the ground. Okay? Still haven't answered the question yet, correct? Okay? So how now, brown cow, are we going to answer the question? The question of how far away did that ball lay? Into what? Or in which one? Because we've got two functions. In this one? In which part? The y? What's going to happen? We already know the answer to that one without plugging it in. If I plug in 2.088 into this function, into the y part of this function, what am I going to get? I'm going to get 0. So I plug in the x. So I want to know how far away it landed, right? Okay. And horizontal distance is the x. Okay. So option number 1, or sub option number 1, I should say. Answer options. Okay. What would be another sub option to find the answer? Go back to the trace, right? And we could type in 2.087729 into that, right? Okay. So we've got two options here. Okay. I will show them both to you. Okay. So I can click on that to get back to my graph. I'm already at that one. So I want 2.087729. And it takes me to pert near 0. Yes? Okay. Option number 2 is I can start another page. This time I want a calculator, and I can go 36 cosine of 58 degrees times 2.087729. And I get the same. So there's the answer to our problem. Okay? We're going to tweak that same problem. This time, he's going to throw it at an angle of 43 degrees and 55 feet per second. I want you to find me the maximum height of the ball and how far that he can throw it. Okay? So, you should be able to use the same ones, just change the numbers. You know what I mean? Hit tab and just go change numbers is all you should have to do. Make this big now. All right, so this is the path. This is the way. Here is maximum height is going to be 27.984 feet, and that happens at t equals 1.172 seconds. The ball is in the air for 2.494689 seconds. Okay? So then option number 1 is we stick that into the X of our parametric and we get 100.348 feet. Option 2 is we can trace it to that value and we get 100.348 feet. So the maximum distance, or the ball is thrown, $100.348. Questions, comments, concerns, clarifications? Good times. Good times.